We consider here how to obtain the rate constants for molecular processes, such as the decay of an excited state. It turns out that we need more than one instrument to measure the fluorescence rate constant. Specifically, we need to measure the observed lifetime and the fluorescence quantum yield. This procedure will be crucial to your laboratory experiment in class. The intrinsic lifetime for an excited state is given by a single exponential with time constant tau observed. The observed rate constant is the inverse of the lifetime. Lifetime is also known as the time constant. This is true because fluorescence decay is a first-order process. We can also write the single exponential fluorescence decay in terms of K observed, the observed rate constant, also K obs. This is not the same as the intrinsic fluorescence rate constant or fluorescence time constant. Here we see the two quantities we need to measure to determine the intrinsic fluorescence rate constant. These are the fluorescence quantum yield and the observed decay rate constant. The quantum yield is a number between 0 and 1 that represents the fraction of molecules that follow a particular path back to the ground state. In the most general case, there are two competing processes: emission of light by fluorescence and non-radiative decay. Hence, the quantum yield is really nothing more than the ratio between, for example, Kf, the fluorescence rate constant, and Kf plus Knr, the total rate constant for decay of the excited state. We can also see that the total rate constant is the sum of the fluorescent and non-radiative rate constants. In general, it is the sum of all processes that cause the excited state to decay. And that is why simple measurement of K obs, or tau obs, the inverse of K obs, is not sufficient to determine Kf uniquely. It determines the sum of Kf and Knr plus any other processes that may also be occurring. We see that with two measurements, we have two equations and two unknowns. We can solve for Kf, the intrinsic fluorescence rate constant, from these two equations. The radiative rate constant is also known as the intrinsic fluorescence rate constant. We can obtain the intrinsic rate constant from the measured quantities as follows. The quantum yield phi is equal to Kf over K obs. Note that K obs is Kf plus Knr, and in this case, that's the total number of paths back to the ground state. There are only two. So it's a fraction that depends on how big Kf is relative to Knr. Then we can solve for Kf in terms of two things we can measure. Kf equals K obs, that's the observed rate constant, and phi f, the observed fluorescence quantum yield. Quantum yield is the fraction of molecules that decay by a particular path. We can make an analogy to a bucket filled with water that has two holes in the bottom. These holes represent the paths. If one hole is larger than the other, then clearly more water will flow through that hole. The rate constants for water flowing are Ka and Kb. In this drawing, Kb is greater than Ka, so a greater fraction of the water will be in the cup labeled B. The exact ratio is clearly given by the ratio of the rate constants shown. Note that the sum of both quantum yields should be equal to 1. If an additional path is accessible, the observed rate constant will become the sum of three rate constants. We have called the third rate constant K other, which could be quenching, electron transfer, energy transfer, or intersystem crossing. In the case of quenching, we can separate the quenching rate constant Kq from the non-radiative rate constant because quenching is bimolecular and depends on the concentration of the quencher. The quantum yield will also be affected by any additional process that we've considered in the previous slide. A process that increases the observed rate constant will decrease the fluorescence quantum yield. This fact has been used to measure rate constants for processes such as energy and electron transfer, in addition to quenching that we will measure in this lab. This slide shows a Jablonski diagram that indicates two of the pathways that can result in decay of a singlet state back to the ground state. Aside from fluorescent decay and non-radiative decay, the diagram also shows quenching and energy transfer.